So thanks for giving me an opportunity to give this presentation. So I wanted to talk about something which kind of puzzles me, or I really like to think about this topic or this challenge. So usually, I mean, in algorithms we think about worst case kind of analysis, which essentially states what is the really worst possible performance of an algorithm on a given input side. But like when you take most of the algorithms and you run them in practice or kind of your real data, then you see it doesn't really, it's not really the case. So worst case rarely describes how your algorithm behaves in real world. Yeah, so and I mean there might be many different reasons, and I will try to show like one of the reasons for this that there is a difference, and there is a kind of a need to go beyond worst case, meaning to really understand or develop different better tools to argue about algorithmic complexity. Yes, and kind of the research on beyond worst case can be applied to clustering, linear programming, even into some machine learning problems. So we start to understand some challenges with this respect. So, like my outline of my talk is I will talk about power law graphs and triangle counting in power law graphs. I need to show you somehow one of the possible approaches to argue about real-world performance of some algorithms, and at the end I will point to some challenges, very general ones. Yeah, so what is a power law graph? I mean, this is something intuitively like the definition and how people understand the definition. It's an undirected graph is called power law with parameter alpha if the fraction of the vertices degree k is proportional to k to minus alpha. Yeah, so this is kind of intuitively clear, but I mean, it's unclear how to apply it to kind of arguing about algorithms. So what should be the right definition? I mean, kind of that you can use in an algorithmic way. I mean, it shouldn't really be like applied in a straightforward way. I mean, what's important about this kind of definition and then about this power law graphs, it's not the case that they are kind of sparse or planar or whatever, that they have some additional structure. I mean, we rarely can say anything more than this degree distribution. And so some vertices have low degrees, most of them, but some of them have very high degrees. And essentially, if you look on almost all kind of real-world graphs, like big graphs, then it seems that they follow power law. Yeah, so it would be interesting to see whether this notion of power law graphs can be exploited in an algorithmic way. Yeah, so this was one of the challenges we kind of took in one of the papers, and it ended to be quite interesting, because I mean, when we really looked on power law graph from algorithmic perspective, we have seen kind of observed new structural properties of power law graphs, and we were able to actually give better algorithms for example, triangle counting and other problems. And something which I find really interesting was we kind of observed that some of the algorithms are structure oblivious. And actually, these algorithms are the typical ones used in some heuristics for example, triangle counting. So actually, it appeared that I will explain what the structure oblivious means in 2 slides. But essentially, the algorithms can exploit the structure of the data, even if they don't know that such structure exists. Yeah, so it might explain why some heuristics work really well on power law graphs and real world data. Yeah, so I gave this typical definition, but it's really unclear how to apply it. So what we did in kind of our approach was to relax the definition. Yeah, so to kind of relax the definition of this proportional to k to minus alpha. And what we did, we actually counted the vertices, the degrees of vertices belonging to some range. And we call this range a bucket. So this bucket is kind of of exponential size, depending on the degree. Yeah, and we only say what we require from the graph is that there is some upper bound on the number of vertices in each bucket. Yeah, and kind of this is a new definition, which is slightly more complicated, but it's way nicer from the algorithmic perspective. Yeah, because so what we say is the graph is called power law bounded with parameter alpha if for every d the number of vertices such that they have degree in this range 2 to the d and 2 to the d plus 1 is at most kind of proportional to the sum of exponents. So essentially we just take the power law distribution and sum it up in this range. Yeah, so it kind of summarizes or kind of relaxes the notion we had previously. And what's kind of important is that if you look on real world data, then essentially every graph we could find fits this definition with a constant of 5. Yeah, so essentially they follow the definition. And now what's important, I mean, this is kind of a worst case definition. Yeah, so if we just, I mean, you can take a real world graph and then check whether the definition is satisfied. And when it is satisfied, then maybe we can somehow use it. So first kind of consequence of this is that we get an upper bound on the number of edges in the graph. Yeah. So the number of edges depends on this alpha and kind of decreases when the alpha gets higher. I mean, another thing which one can observe is that like we can derive a slightly kind of stronger bounds on the number of edges when this graph is kind of a simple graph. So when we can cast this power law graph into a simple graph, and then we can get an even better upper bound on the number of edges, which is given here. Yeah, because and the argument is that there are at most n to 1 minus alpha high degree vertices, so there can be at most n to 2 over alpha edges between high degree vertices. Yeah, and then every other edge is incident to a low degree vertex, and the total degree of low degree vertices is n to 2 over alpha as well. Yeah, so you get some already via the definition and doing the counting. I mean, if your graph is power law bounded and simple, then it has less edges, even less edges. Yeah, and what is the triangle counting, and what was kind of our observation? So in triangle counting problem, you are given undirected graph, and a triangle is a set of vertices such that each pair of vertices is connected by an edge, and the problem is to compute the number of triangles in the graph. And there was already some previous research on this topic. I mean, you probably all know this first algorithm 2/3/2, which just kind of is a folklore algorithm, but there were some improvements using matrix multiplication. People actually looked on power law graphs in different models and tried to develop like faster algorithms that would take into account the structure of the graph. And somehow where we came in, the kind of state of art was this Barry algorithm that assumes that we are given a random PLB graph. Yeah, so power law bounded graph. But I mean, somehow the challenge for us was to move kind of this approach to worst case guarantees. Yeah, because I mean, essentially, if somebody gives you a internet graph or whatever, I mean, you just have one instance of this graph, and then how you should check that the graph is random. I mean, essentially cannot. So if one would give you this function, get a random number, and then says you can call it just once, and then certify that this is a random number, I mean, you cannot really do anything. And so essentially this result that assumes that the graph is random, I mean, they really does not imply anything on running time of real world graphs. Yeah, so kind of our approach was to really come up with this new definition and then analyze kind of this the standard algorithm and show that under this much weaker and realistic assumption, it works in the running time, which kind of is faster. And what's important, I mean, this is a standard algorithm that doesn't even know what is alpha in the exponent, and it still works faster. So essentially, this alpha is only considered in the analysis of the algorithm. So the algorithm is structure oblivious. So even if it does not know that the data has some additional property, it's power law, it still works faster. And we considered the standard algorithm. Yeah, so if you're given a graph, then you look on every vertex and direct each edge towards endpoint of the higher degree. And then you go over each vertex and only consider the pairs of out edges. Yeah, and check if they form a triangle. And this is exactly, we proved that under this PLB assumption, under this worst case assumption, the algorithm works in the time bound given here. Yeah, so essentially this analysis applies to all kind of real world data, for example, coming from the Snap graph library. I mean, this approach kind of raises interesting questions. For example, what other problems have better solution of power or low graphs? Are there other useful properties of real-world graphs that we could could use by algorithms, or can those properties be defined in a worst-case way? Because usually people apply kind of stochastic or random assumption to graphs, and it would be interesting to have worst-case definitions. Another kind of things which is very interesting, and it's kind of highly related to this topic. It's the notion of learned data structures. So in learned data structures, we kind of try to. I mean, we do not come up by ourselves with the right model, but rather build an ML algorithm, even a neural network that would kind of model the data. And then we try to exploit this ML model using standard algorithmic tools. For example, like kind of one of the most important example is kind of the index data structure, which essentially in like the dictionary. So you want to check whether in your data set there is a given key. So what people do and try to do here is to actually use prediction models, for example, neural network to point to the right element in this data structure in order to actually speed up the computation. And so let me maybe skip this slide. So I think this is a really interesting topic of research. I mean, there are kind of new models of typical instances. And people come up with really interesting kind of tools, algorithms, and importantly, these things at the end finds application in practice. So you can actually argue about some algorithms that it works better or worse in practice. If you are interested to learn more, then I recommend this book by Tim Ravgarden, which appeared this year actually. It's called Beyond the Worst Case Analysis and shows like many different topics. And you might check as well the Tim's talk on Graphite Algorithmic Colloquium, which was on 25th of March. Thank you.